Hello everyone and welcome back to the series of digital logic design, and today we will study about carry look ahead adder. The addition of two numbers in parallel implies that all the bits of the augment and addend are available for computation at the same time, like we have done in a ripple carry adder, in which the bits of addend and the augment all were available, but the missing thing was the carry. So before starting carry look ahead adder, we will study the factors or the features which were affecting the performance of ripple carry adder. And for this, we will study the carry propagation. Now, in any combinational circuit, the signal must propagate through the gates before it gives us the correct output sum at the output terminals. Now, the total propagation time is equal to the propagation delay of a typical gate multiplied by the number of gate levels in a circuit. So if we are computing what will be the total delay factor in a circuit, it will be equal to how much time is taken by a gate into the number of gate levels, where the longest propagation delay in an adder is the time it takes the carry to propagate through all the full adders. This was the issue in a ripple carry adder, that for exact output we have to wait for the output carry which propagates from input carry and takes some time for true answer. Now consider the given circuit of a ripple carry adder. In this, each bit of some output depends on the value of input carry, and the value of Si at any stage in the given adder will be in its steady state final value only after the input carry to the stage has been propagated. Like if you consider output sum bit S3, the bits of A3 and B3 are available as soon as the input signals are applied. However, the input carry C3 doesn't settle to its final value until C2 is available from the previous stage. Similarly, C2 has to wait for C1 and so on down to C0. Thus, only after the carry propagates and ripple through all the stages, then the last output S3 and carry C4 will settle to its final and the true value. Now, the number of gate levels for the carry propagation can be found from the circuit of the full adder. Now, the circuit of full adder is redrawn with the different labels in the figure for convenience. Now, the input and output variables use the subscript I to denote a typical stage of the adder, and the signals at Pi and Gi settle to their steady state values after they propagate through their respective gates. And you can observe in the figure that a full adder is being implemented with two half adders. Now, these two signals of Pi and Gi are common to the all half adders and depends on the input augment and addend bits. Now, the signal from the input carry Ci to the output carry Ci plus 1 propagates through an AND gate and an OR gate, which constitute two gate levels. And if there are 4 full adders in the adder circuit, then the output carry C4 would have 2 into 4 equals 8 gate levels from C0 to C4. So we can say that for a n bit adder, there are 2n gate levels for the carry to propagate from input to the output. The carry propagation time is an important attribute of the adder because it limits the speed with which the two numbers are added. Although the adder, or for that matter any combination circuit, will always have some value at its output terminal, but the output will not be the true or the correct unless the signals are given enough time to propagate through the gates connected from input to the output. Since all other arithmetic operations are implemented by successive addition, so the time consumed during the addition process is the critical one. An obvious solution for reducing the carry propagation delay time is to employ faster gates with reduced delay time. But however, the physical circuit have limit to their capability, and practically the gates may have certain amount of time delay. Another solution is to increase the complexity of the equipment in such a way that the carry delay time is reduced. For this purpose, several techniques are available for reducing the carry propagation time in a parallel adder, and the most widely used technique employs the principle of carry look ahead logic. Now we will construct the adder circuit with the help of carry look ahead adder. And for this purpose, we will define two new binary variables. One will be known as carry propagate and second one will be carry generate. Carry propagate will be equal to the exclusive OR operation of input and AND bit, like PI will be equal to AI exclusive OR with BI, where the carry generate will be equal to the product of AND and the AND bits. GI will be equal to AI dot BI. Now using the substitution of these new variables, the output sum and the carry will be equal to SI will be equal to PI exclusive OR with CI, and the next stage carry will be equal to CI plus 1 equals GI plus PI dot CI. Now the carry generate or GI, it produces a carry of 1 when both AI and BI are 1 regardless the value of input carry. Where the carry propagate or the PI, it determines whether a carry into stage I will propagate into stage I plus 1, which means that an assertion of carry CI will propagate to an assertion of CI plus 1. Now using the substitution, we will write Boolean functions for the carry output of each stage and will substitute the value of each CI from the previous equations, like C0 will be known as the input carry, then C1 will be equal to G0 plus P0 into C0. Similarly, the equations for C2 and C3 will be found. Now if you observe the equation from C1 to C4, the Boolean functions for each input carry is expressed in the sum of product form, and each function can be implemented with one level of AND gate followed by an OR gate and results in a two-level implementation. Now here important thing to note is that the equations of C1, C2, C3 and C4, all these equations are dependent on carry propagate, carry generate and the input carries, where the carry propagate and carry generates are calculated with the help of AND 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 bit, so this information is available, and input carry is applied to the adder, so this information is also available. Unlike the ripple carry adder in which C3 has to wait for C2 and C2 has to wait for C1. In this scheme of adders, all the carries are calculated at the same time because all the information is available. Now the three Boolean functions for C1, C2 and C3 are implemented in the carry look ahead generator, which is shown in the figure. Note the circuit can add in the less time because C3 doesn't have to wait for C2 and C1 to propagate. In fact, C3 is propagated at the same time as C1 and C2 because all the equations are implemented in two levels, so the C1, C2 and C3 are available at the same time. This gain in the speed of operation is achieved at the expense of additional complexity of hardware for the given circuit. Now the construction of a 4-bit adder with the carry look ahead scheme is shown in the figure. Each sum output requires two exclusive OR gate, where the output of first exclusive OR gate generate the carry propagate variable PI and the AND gate generate the carry generate variable GI. The carries are propagated through the carry look ahead generator and are applied as input to the second exclusive OR gate. Now all the output carries are generated after a delay through two levels of gates. Thus, the output S1 through S3 have equal propagation delay times. In the given scheme, the two-level circuit for the output carry C4 is not shown. This circuit can be easily derived by the equation substitution method. Now, if we make comparison of this scheme with ripple carry adder, in ripple carry adder, for addition of 4-bit, the carry propagation delay time was about of 8 levels, where in case of carry look ahead adder, 2 levels are required for the generation of carries, where 1 level is required for carry propagate and carry generate, and further 1 level is required for the output sum. So the total levels will be equal to of 4 level delay, and wherein ripple carry adder it was about 8 levels delay. And this is achieved on the cost of complexing the gate structure. Thanks for watching the video and stay connected for more interesting videos.